We begin this lecture by introducing the effective value of a periodic signal, which will be very useful in power computations for circuits in sinusoidal steady state. Okay, to motivate us to define the effective value of a periodic signal, let's consider two separate cases. Consider the following two circuits. Okay, in the first circuit we have just a current source and a passive resistor, LTI resistor, whose resistances are. Okay, we're going to call this circuit the AC circuit because the current source, the input that's driving this resistor, is an AC signal. Okay, it's a periodic signal. So we have I t plus t equals IT. So it's a periodic signal, and for this circuit, for this resistor, the instantaneous power can simply be computed as the product of the current and voltage of the resistor. Okay, it's just power dissipated on the resistor is P of t equals I of t times V of t plus minus, and V of t is R times I of t. Therefore the power, the instantaneous power, is R times the resistance times the square of the current. So what we have is R I t square. Okay. Now since I of t is periodic, its square is periodic also. So that means the instantaneous power is periodic signal. Whenever that's the case, it's interesting to have a look at its average value. And average power is defined as P average, which is you integrate it through one period and then you normalize it with the length of the period to obtain the average value. Okay, pt dt. Okay, now let's also consider a much simpler case. Again, we have the same topology, but this time the input in the circuit is a DC, okay, a constant current I. So let's call this therefore the DC circuit. And we're working with, let's say, resistor with same resistance, okay, both are R. Now I is positive, suppose, and it's constant. Okay, when I is constant, the power of the instantaneous power of the resistor is also constant. Since it's constant, it equals its average value. Okay, so we can write P of t equals P average, and that equals R times I squared. Okay, now suppose that the average power dissipated on the resistor in the AC circuit equals the power dissipated on the resistor in the DC circuit. Okay, under that assumption, let's try to figure out a relation between this positive number I, the value of the current in the DC circuit, and this signal I of t, the current in the first AC circuit. Okay, suppose the average powers are equal for both circuits, for NAC and DC. And here is the question we ask when that condition is satisfied. What does the above condition imply? Okay. In other words, what relation there must exist between, if that assumption holds, between this constant number I, let's say 12 amps, and this current, which is a periodic time varying signal I of t. For that, all we have to do is we equate the average powers. Here it's constant, here it's r times I square, and here it's computed through this integration. Okay, so we therefore have 1 over t from 0 to t r I t square dt. So that's the average power for the AC circuit, and we're told that this equals the power, both average and instantaneous, because the current source is constant, in the second circuit. Now these r's, they cancel, and immediately we obtain the relation between the current, the constant current I, and the time varying signal I of t. In other words, we have 1 over t 0 t I t square dt. You take the square, you integrate it, and then you normalize with the length of the interval of integration, and then you take the square root, and that gives you I, this positive constant in the second circuit. And this motivates the following definition. Okay, here we're going to define for a given periodic signal its effective value, or equivalently its root mean square value. Okay, root mean square value. Okay, here is the definition, and this definition will be very useful when we soon start talking about power computations in circuits in sinusoidal steady state. Given a periodic signal, I t equals I t plus capital T being the period, the effective or equivalently root mean square RMS. Okay, so root mean square value I, and we write in a subscript EFF for effective, or sometimes we write RMS for root mean square, is defined by the following identity. Okay. I effective square equals 1 over t from 0 to t I t square dt. Okay, and notation is such that usually time varying signals are represented by lowercase letters, and when we talk about their effective or RMS values, what you do is you capitalize the letter, it could be current or voltage, and then you put as a subscript either EFF or RMS. So that's our definition of effective value for a periodic signal. Now, of course, we will almost exclusively be interested in sinusoidal signals, so that very important class of periodic signals. And for that, let's emphasize that for a periodic signal with amplitude A, the effective value equals that amplitude divided by square root of 2. Okay? And that's easy to show, so that's left as an exercise. Show that for IT sinusoidal signal, A cosine omega t plus phi, we have I RMS or I effective equals, okay? Now effective value for a periodic signal does not depend on the frequency of oscillations, does not depend on the phase of the sinusoidal, it only depends on the amplitude, okay? And it equals the amplitude divided by square root of 2. Okay, now having defined effective value for a periodic signal, we're now ready to start talking about powers of, in particular average powers of components, certain components like resistor, inductors and capacitors that belong to a circuit, an LTI circuit in sinusoidal steady state. Okay, so instantaneous and average power for circuits that are in sinusoidal steady state. Okay, let's begin by the resistor, okay, and then we're gonna extend what we find here to capacitor, inductor, and then to a general one port eventually. So suppose that this is some LTI resistor that's part of a circuit, LTI circuit that's in sinusoidal steady state, okay. So this indicates it's the voltage V of t, this is the current of the resistor, and R indicates the resistance. Okay. Suppose that the current equals some magnitude which we denote by Im. Okay, this is a positive number. Cosine omega t plus some phase. Omega is the frequency of oscillations in our circuit that's in sinusoidal steady state. Now, clearly this signal is periodic. Okay, period t equals 2 pi over omega seconds, and the RMS or effective value for this current is, from this exercise, the magnitude divided by square root of 2. Okay, we have Im over square root of 2. Now let's, for this component, compute both the instantaneous power, and once we have the instantaneous power, we can also talk about its average value. Okay. Now, by definition of instantaneous power for any single branch element, we have P of t equals the product of current and voltage. Okay, P of t equals IT Vt. And that equals R times Im cosine omega t plus phi. Okay, so R times I, that's V, and we have another I, so that makes Im cosine omega t plus phi. Basically, what we have is R times IT squared. And now that can be written as, here we have two cosines multiplying one another, and using the trigonometric identity, which is cosine square alpha, can be written as 1/2 1 plus cosine 2 alpha. Okay, this can be written as a constant term plus a sinusoidal term. So if we do that, we can rewrite P of t as that equals 1/2 RIM squared. Then that's multiplied by using that identity 1 plus cosine 2 alpha. This is our alpha, omega t plus phi. Therefore, we have 2 omega t plus phi. Okay, so that's the instantaneous power for our resistor. So let's therefore put it here once again. Instantaneous power for this resistor, that's part of a circuit in sinusoidal steady state, equals 1/2 RIM square, Im being the magnitude or the amplitude of the current passing through our component. Then we have 1 plus cosine 2 omega t plus 2 phi. Okay, and this is periodic with capital T. In fact, it's periodic with T over 2, but it's not really important since we're gonna compute the average. Now, once we have the instantaneous power, let's compute the average, which, by looking at this expression, which is more or less obvious what it should be, because the instantaneous power can be written as we just computed, can be written as the sum of two terms. One of those terms is a constant, which will produce itself as its average, and the other term is purely sinusoidal. And we know that purely sinusoidal signals produce zero averages. Therefore, the average power of the resistor must be the constant term of that instantaneous power expression. Which is 1/2 RIM squared times 1. Okay, so the average power for our resistor therefore equals, well, by definition, what we do, we integrate it throughout the period and then we divide it by the length of the integration, which is t. Okay, so that equals pt dt, and that equals 1/2 RIM squared times the integral of this constant term 1, and then the integral of the cosine term. Okay. 1 over t, we have 1 dt from 0 to t plus 1 over t from 0 to t cosine 2 omega t plus 2 phi dt. Okay. So, to see things better, we wrote this integral as sum of two separate integrals. Now, this clearly, we're taking the average of 1, that clearly produces 1. Okay, the average of a constant signal is itself. And here we're taking the average of a purely sinusoidal signal. Okay, so regardless of omega and phi, that will always produce zero average. Okay, so here we have 0, and this equals 1. Therefore, the average power for a resistor in sinusoidal steady state, or circuit in sinusoidal steady state, is 1/2 R times the square of the amplitude of the current passing through it. Hence, P average equals 1/2 RIM squared. Note that IM squared over 2 can be written as IM divided by square root of 2, and then you take the square and Im divided by square root of 2 is the effective value or the RMS value of this signal, I of t. Hence, the average power can be written very nicely in terms of the effective current value. In other words, we have R times I RMS or I effective square. Okay, so that's the average power for a resistor. Okay, now let's move on to our dynamic components, namely capacitor and inductor. Capacitor first. Again, the assumption is such that this capacitor that we will study is part of an LTI circuit, and that circuit is in sinusoidal steady state. Plus minus Vt voltage, C the capacitance, and this is the current passing through our component. Let V of t, the voltage of our capacitor, is this magnitude Vm, and then cosine omega t plus phi, omega being the frequency of oscillations in our circuit that's in sinusoidal steady state. As before, we have the period t equals 2 pi over omega seconds, and the effective value of the voltage is this magnitude divided by square root of 2. Okay. Now, once again, what we're going to do is we're going to look at the instantaneous power and its average. So for that, we need the current information, which we can easily figure out using phasors. The phasor of the current, I, equals the impedance, the admittance times the phasor of the voltage. The admittance of the capacitor is J omega C. J omega C times the phasor of the voltage V. Okay. So that equals J omega C. What's the phasor of V? This is our V. This is the magnitude. And the phase is phi. Okay. And then this equals, therefore, this J can be written as, in polar form, a complex number with magnitude 1 and phase pi over 2. Therefore, the overall magnitude will be omega C Vm, and the phase is phi. Okay, so that's the phase of the voltage. To that we add 90 degrees plus pi over 2 radians. Okay, for resistor, voltage and current, they are in phase, but for capacitor, the current leads the voltage by 90 degrees. Okay, therefore I of t, the time domain signal, the time domain current, equals a sinusoidal with magnitude omega c Vn, and phase is written here phi plus pi over 2. Omega c Vn cosine omega t plus phi plus 90 degrees. Okay, so we have the voltage, we have the current, therefore we can easily compute the instantaneous power by simply taking their product. Okay, so let's do that. P of t, the instantaneous power for our capacitor, equals IT Vt, the product of current and voltage. And that produces what? We have the current here, the voltage here, and the current here. And that reads omega c voltage magnitude square. Then we have the product of two cosines. times cosine omega t plus phi plus pi over 2 radians. Okay, and that can be written as, by using, okay, let me squeeze it here, by using the trigonometric identity cosine alpha cosine beta can be written as 1/2 cosine alpha plus beta plus cosine alpha minus beta. Okay, using that identity we can now re-express this product of cosines and have 1/2 omega c Vm square, okay, times cosine alpha plus beta, which produces 2 omega t plus 2 phi plus pi over 2, and then plus cosine alpha minus beta. Now alpha minus beta is either pi over 2 or minus pi over 2, but either it's plus or minus, its cosine is 0, therefore we will only have a single cosine term when we apply this identity to our instantaneous power for the capacitor. Okay, so this is our instantaneous power P of t, which immediately gives us the following average. Now, for the resistor, what we had a sinusoidal term and a constant term. Purely sinusoidal term produces 0 average, and the constant term equals its own average, equals itself as its average. Therefore, we had something non-zero for the resistor. But this time for the capacitor, the instantaneous power is purely sinusoidal with no offset, no DC component. Therefore, its average directly is 0. Okay, so that equals 0. Because PT is purely sinusoidal. Okay, so let's compare therefore two things, the resistor and the capacitor. That's part of a sinusoidal steady state. The resistor produced, okay, we're talking about a passive resistor, okay, R is positive. So resistor produced something positive, okay, something non-zero for the average power. So that means in the long run, resistor is always extracting electrical energy from the circuit. Whereas for the capacitor, the average power is 0. So that means during some times, the capacitor is extracting energy from the circuit, so it's storing energy, and some other times it gives back the stored energy in the previous times, okay? And then that giving and taking balances themselves perfectly, and in the average we have 0 power, okay? Now, speaking of stored energy, let's also talk about that for the capacitor, okay, because it's a component that's able to store energy. So how about stored energy for the capacitor? Now, E of t, the stored energy for a capacitor, equals 1/2 C times the square of the voltage across its terminals. That is, we have 1/2 C Vt square, and that equals 1/2 C, the magnitude and cosine square omega t plus phi, okay, because V of t is given as that sinusoidal signal. So that's the instantaneous or stored energy at time t, okay, in the circuit, and this signal is periodic with the same period as the voltage, okay, because we have the voltage square here. Therefore, we have the following average stored energy for the capacitor: 1 over t 0 to t et dt equals. Now we have cosine square here, which can be written as, so that's cosine square alpha, which can be written as 1/2 plus 1/2 times cosine 2 times this thing. Now, that 1/2 is a constant term, okay? And it will give us something non-zero. The other term, the purely sinusoidal term, will produce 0 average. And therefore, what we have is this thing, the magnitude, times 1/2, that constant term. So 1/2, another 1/2, that makes 1/4. C times the magnitude square for the voltage. And then remembering that the effective value of the voltage is that magnitude divided by square root of 2. We can write this in terms of the effective value of the voltage as 1/2 C V effective square. Okay? Which is a little bit nicer because it has the same form as the instantaneous stored energy identity, 1/2 CV square. Okay, now let's also talk about the dual component, namely the inductor, and then we're going to generalize to an arbitrary one port. So this is our inductor. That's part of a circuit in sinusoidal steady state. V of t, I of t, L, the inductance. Okay. I of t equals the following current, some magnitude, and then we have cosine omega t plus phi. Period. T is 2 pi over omega seconds, and the effective or the RMS value of the current is the magnitude divided by 1.4 Im over square root of 2. Now, by duality, what we can do is we can just remember our analysis for the capacitor and replace current with voltage and inductance with capacitance, and capacitance with inductance, and we have the results that we are after. So by duality, in other words, we can write the instantaneous power equals 1/2 omega L I M square cosine 2 omega t plus 5 plus pi over 4. That's our instantaneous power. It's a purely sinusoidal signal, therefore its average is 0. P average is 0. Okay? And as with capacitor, there is something that's non-zero, and that's the average stored energy. This is instantaneous stored energy, 1/2 L I M square cosine square omega t plus phi. Okay, this cosine square can be written as 1/2 plus some purely sinusoidal term whose average will be 1/2. Therefore, the average E of t will be this thing times 1/2. E average equals 1 over 4 L. Then you square the magnitude of the current. And in terms of the effective current of the inductor, this can be written as 1/2 Li effective, or I RMS square. So that's the average stored energy in an inductor that belongs to a circuit in sinusoidal steady state. Okay. Now let's talk about an arbitrary one port that belongs to a circuit in sinusoidal steady state. Okay, power into a one-port circuit. Okay, suppose this box represents our one-port circuit, denoted by N. We have V of t and we have I of t, the voltage and the current. So let I of t equals Im cosine omega t plus some phase, which we denote by phi I. And V of t is again a sinusoidal signal with some magnitude and some phase, omega t plus phi v, let's say. And then taking the product immediately gives us the instantaneous power. In other words, P of t equals Im Vm, and then we have the product of two cosines, cosine omega t phi I and cosine omega t phi v. Okay. Now, using the identity that we have already used, that is the product of two cosines can be written as sum of two cosines divided by 2. Namely, cosine alpha times cosine beta equals cosine alpha times cosine beta equals 1/2 time cosine of the sums and the cosines of the difference. So this equals therefore 1/2 Im Vm, then cosine of the difference, which is phi v minus phi I, or phi I minus phi v, depending on which one you take alpha and which one you take beta, but it doesn't really matter because cosine is an even function. Okay. Plus, okay, plus what? Plus 1/2 Im Vm, then we have the cosine of the sums, namely cosine 2 omega t plus phi I plus phi v. Okay, now this is a purely sinusoidal term, therefore it will produce zero average. Okay, so this has zero average because it's purely sinusoidal, and this is constant, meaning its average equals itself, therefore the average power simply equals this term here. Okay, therefore P average reads 1/2 times the product of the magnitude of current and voltage signal, and then this term, which is the cosine of the difference of phases of voltage and current. And in terms of effective values of voltage and current, this can be written as I effective times V effective times this factor, cosine phi v minus cosine phi I. Okay. So this is the average power for a one port, which equals the product of the effective values of voltage and current times this factor, cosine of the difference of phases for voltage and current. For resistor, since the voltage and current were in phase, this term was as high as possible, namely 1. And we had I effective times V effective for the average power of the resistor, which can be written as R times I effective square. For inductor or capacitor, the difference between the phases was pi over 2 or minus pi over 2. Both produced zero cosine. Hence, for capacitor and inductor, we had zero average power. And now for an arbitrary case, one port, where inside we may have many resistors, capacitors, and inductors. This phi v and phi I could be anything. And then, depending on the relative phases, okay, of voltage and current, the P average reads this expression. Now, because this term is important, it's given a name, and it's called the power factor. When the one port is passive and it doesn't contain any independent sources inside. Okay. The term cosine phi v minus phi I is called the power factor. Okay. When n is, or one port is passive and independent source free. Okay, there are no independent sources inside. Now, let's look at this average power expression from the impedance point of view. Note that if this assumption is satisfied, that is, if there are no independent sources inside, and then it can be represented, at least from the terminals point of view, current voltage characteristics point of view, by an impedance. Okay. Now, suppose n contains no independent sources. And therefore, for the phasor domain circuit can be represented by an impedance. Its input impedance. Okay. Z. By definition, Z is the ratio of voltage to current at the port terminals. Therefore, we have V equals Z times I. V and I, they are the phasors of this voltage and current, respectively. Now, the following observations are easy to make. We can write Z equals, let's write voltage and current in terms of polar coordinates, okay, polar representation. The voltage is this, the magnitude Vm phase phi v, and the current is this, Im phi I. So that reads Vm over Im with phase, this difference, phi v minus phi I. Okay. This is the magnitude of V and this is magnitude of I. Therefore, their ratio must be, from this formula, their ratio must be the magnitude of Z, the impedance. This can be written therefore as Z with phase phi V minus phi I. Okay, then what? Then we can write P average equals 1/2 Vm Im cosine phi v minus phi I. Okay, so we're using this formula that we obtained here, and that equals 1/2 In times, now instead of Vm we can write In times the impedance Z, the magnitude times the impedance Z, and then we have the cosine term. Okay. Hence, okay. Well, that can be written as 1/2 Im squared times the magnitude of Z times cosine phi v minus phi I. Okay. Now, let's interpret what that means. Which is very easy to do. All we have to do is we have to use this z equals that is z is a complex number whose phase is phi v minus phi I. And here that same term phi v minus phi I appears here. And this, since this reads magnitude of z times cosine phi v minus phi I plus j sine of phi v minus phi I, this must be the real part of our impedance. Okay, therefore the average power for a one port that doesn't contain independent sources equals 1/2 Im squared times the real part of its impedance, which we called the resistance. Okay, hence P average equals 1/2 Im squared times the real part of z. Okay, this thing is the real part of our impedance. And in terms of the effective value of the current, it can be written as I effective square times the real part of the impedance or the resistance of the one port. Okay. Likewise, we could have expressed the thing in terms of the voltage, and if we do that, we have P average equals 1/2 Vm square times the real part of 1 over z, okay, the admittance, and that equals V effective square times the real part of admittance, which we call the conductance of the one port. Okay, this and that, they are equal to one another.